Okay, so lubrication and general bearing. Okay, so first we have to classify the different types of the lubrication. Okay, so it can be classified in the hydrodynamic, hydrostatic, and the elastomhydrodynamic boundary and the solid field. Okay, in the solid field. Okay, so let's use an example of this engine and the piston. Okay, so if we just disassemble this transmission or this engine parts, and we tell what's the parts of the or which portion of the components belongs to what type of the lubrication is? Can we tell that? Can we tell that? Can you tell that? Okay, so for example, for this piston, right? For this piston part, we have a connecting rod, right? We have the connecting rod, which is for the open and close the piston valve, right? For the piston valve. Okay, so for this rod or this shaft, this shaft, this main crankshaft, we as the gasket, okay, and this gasket is soft, okay, it's soft. Therefore, this contact is being with two surface, hard surface and soft surface. Okay, so this whole component drawing is like this. Okay, it's like this. This is the crankshaft. It's the main crankshaft bearing connecting to this rod, connecting rod, and the top of it is connecting to the piston. Okay, the piston. Okay, okay, and this shaft bearing will install with this engine block, and between them we need a gasket. Okay, or we need a groove. We need a gasket or a groove to increase the bearing lubrication. Okay, okay, okay. So for this lesson, we are gonna discuss what type of this lubrication that can be applied to the different components. Okay, different components. Okay, so we see the soft gasket here. Okay, and this is the man crankshaft. Okay, so we're gonna put this lubrication between this. Okay, between this crankshaft and this soft connecting rod. Okay. Okay, so that's defined. That's why I mentioned previously. We have to define the different type of the lubrication, right? Depending on its thickness and the friction coefficient. And this friction coefficient is related to the film thickness, or say the lubricant thickness. Okay, so if this thickness is thinner, okay, and its friction coefficient will increase, it's gonna be higher. Okay, and we define this lubrication type as boundary. Okay, and if this film thickness, or say the lubricant thickness, is thicker enough, okay, we define its lubrication type as hydrodynamic, and it's a mixed lubrication in between. Okay. Okay, so give this example. It's a water ski. Okay, it's a water ski. If it is the boundary lubrication, okay, opposing surface meet with little or no separation. So there are two surfaces, right? Surface 1 and surface 2. Okay, so for the surface 1, in this case, right, it's your ski, water ski. And the surface 2 is the water, right? And in between is the lubricant. Okay, so if this opposing surface 1 and surface 2 meet the little and no separation, we define it as the boundary lubricant. And in this case, it occurs at low speed. So you can think of this boat or kayak cruise in very low speed. So if you're a water skier, you will feel your water ski, the board is exactly contact to the water surface. Right? Okay. And the mixed lubricant. That's mean the two surfaces with moderate thickness. Okay, so this thickness is defined as the lubricant thickness. And it is a transition from low to high speed. And the asparagus occasionally come in contact. Okay. Okay, so if the cases with the high speed, moving parts are completely separated, right? That means the ski board and water is separated with a thick film. So you can think of this boat or this kayak cruise very fast, and these two surfaces separated, right? This surface and this surface separated. They separated. Okay. Okay, so therefore we can define for this very thin film lubricant between two surfaces, it defines the boundary lubricant. Okay, and these two surfaces with the a moderate thickness, we define it as the mixed lubrication. And if this two surface has the very thick thickness of the lubricant, it can be defined as the hydrodynamic, right? Hydrodynamic. Okay. So I'm using this case to explain how to define the type of a lubricant. Okay, it's roughly. Okay. It's roughly. Okay, so first, the hydrodynamic lubrication, also called the full film or fluid lubrication. Relatively thick film of lubricant prevents surface contact and does not depend on external pressurization of the lubricant. And few pressure is created by moving surface pulling the lubricant into a wedge-shaped zone. Requires a sufficient velocity to create the pressure to separate the surface. Okay. So if we have this general bearing, okay, okay, and these two surfaces, the shaft and the bearing, between these two surfaces have this lubricant oil. So when this shaft is rotating, this oil will be squeezed in a specific direction, and it be called the wedge. Okay, it be called the wedge. So therefore, for this static condition, right, this shaft have the weight, gravity, right? And when this shaft start to rotating, the wedge shape form. Okay, so when this is rotating, let's see the wedge shape here. Okay, it's the wedge shape. And then when it's rotating, this wedge shape keep changing, and which can be represented to the pressure distribution. Okay, it's a pressure distribution when this shaft rotating, and this wedge shape to support the surface to carry the load, okay, to carry the load. Okay, so the hydrostatic lubrication. Lubricant is introduced under external pressure to separate the surface when a relatively thick film, 1 to 100 micron thick, do not require motion, and used when velocities are small or zero, support high load, highly precise but expensive. Okay, so for this static lubrication, it needs the external pressure to separate the surface. No motion required. That means the zero velocity. And it can support with the high load. And it is expensive. Okay, so for this previous case is hydrodynamic, right? We need the velocity. We need the velocity to form the wedge shape. And this wedge shape can support or can carry the load, right? To carry the load. However, for this hydrostatic lubrication, we don't need the velocity, even though it can be static. But it needs the external pressure to separate the two surfaces. Okay, so for this example here and here, okay, it's the shaft and it's bearing, it's oil, right? So when this is stop, this shaft stop, we need a pump to supply the pressure to keep these two surfaces separated. Okay, so in this case, it's the similar. We need a pressure fluid input to keep these two surfaces separated. Right? And this is the load direction. And this is the pressure profile. It's fluid pressure profile. Okay, we need to provide the pressure, right, to separate these two surfaces. Even this turntable is static. It's not rotating. Okay. Okay. Okay, so the elastomeric lubrication, EHL. Okay, so in this lubrication type, the surface deformations play a key role in development of the lubricant film. So it can be classified into a hard surface and softer surface. For the hard surface, it can be defined by the Hurst contact mechanics. That means it can be hard contact between two surfaces, such as the rolling contact, the gears, and the roller bearings. And for soft, occur when this contact region extends over a substantial portion of the matting surfaces. Okay, so this is examples here. So for this hard contact, right, the roller bearing, which belongs to the non-confocal contact. And for the journal bearing, the two surfaces has the extend surface contact, right? Of extend surface, and it belongs to the confocal contact, and even they can carry the same load as that of the non-confocal contact, because this oil, this lubricant, is incompressive, right? It's incompressive. Okay. Okay, so this is the case. This for the gear contact belongs to the non-confocal and hard EHL. And for this tire, right, it belongs to the soft contact, right? This tire surface with the extend region for the contact area, right? Okay. Okay, boundary lubrication. When conditions do not provide a thick enough lubricant film for hydrodynamic lubrication, and the highest aspects of the surfaces may be separated by few molecules of lubricants. A mixed condition of the hydrodynamic and the boundary lubrication often existed. It's a mix, right? And the viscosity of the lubricant is not as important as the chemical composition. That's mean, wow, for this very, 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 very thin film, well, the viscosity is not important, but the chemical composition. Okay, but the chemical composition. Okay, so the final types of the lubrication is a solid film by using the solid as the lubricant, such as the graphite and the molybdenum disulfide, to create the layer of the solid material, and often use at extreme temperature. And why use this graphite or this called MO molybdenum disulfide, MOS2? Why? Because they are the 2D materials. That means it's the structure of layer by layer, and the bonding between the layers is weak. That means the two surfaces can slide with each other easily. And this mechanism provides this lubrication function, okay, for two surfaces. Okay, let's go back to some mathematics. Okay, first, for this lubrication, the property, okay, we say the property of the lubricant, the most important one is viscosity. Okay, how to define the viscosity? Okay, so shear stress in a fluid is proportional to the rate of changing velocity with respect to y. Okay, so in this case, we can think of the river or a creek. We have the plate on top of it, and we apply a force to put or to draw this plate with the constant velocity u. And this velocity profile, or say the rate of the change of the velocity with respect to the height of this river, y, right? We can define it by this equation. The tau is the shear stress when we pull or draw this plate on the top of the river. Okay, so we can define the velocity profile is u, the lowercase u, and the capital case U is the constant velocity of this plate, right? So we can define the velocity profile, which is a function of y. Okay, so in this case, in this model, it has to be matched by this relation, this shear stress equals to F divided by the A, the shear stress between the plate and the river, the water, right? So by this definition of the shear stress, it's the force divided by the area, okay, which equals to the velocity gradient with respect to y times a constant. Okay, times a constant. And we define the constant is the absolute viscosity or the dynamic viscosity. And for most of the lubricating fluid, the rate of shear is a constant, right? The rate of shear is a constant. Okay, therefore, the du dy is a constant equal to u. The capital U defines the velocity of the plate divided by h. H is the height, or say the thickness, okay, of the river. So the shear stress will equals to the viscosity times, right, the U over the capital U over the lowercase h here. So the fluid exhibiting this characteristic called the Newtonian fluid. If this liquid or this fluid presenting this relation, and it can be defined as a Newtonian fluid. Of course, you have to know what type of the fluid belongs to the non-Newtonian fluid. Okay, non-Newtonian fluid, like two-spliced, right? Like two-spliced. Okay, and this is not in the scope of this course. Okay. Okay, so for this hydrodynamic theory already be developed in early 1880s. Okay, so this is the equipment for this test, for this called the bootstrap test. Okay, so we build up the shaft, right, and the housing or bearing, and inject the lubricant, right, and we apply the distributed load, right, distributed load on top of it. Okay, so this is an experimental setup for this hydrodynamic experiment. Hydrodynamic experiment. Okay, I just want to show you how this lubrication test took in, oh no, 200 years ago. Okay, 200 years ago. Okay, so at this moment, this experiment is not, well, it has been, it's not considered the effect of the thickness variation. Okay, thickness variation. That's been we define when this shaft was rotating, the thickness between two surfaces is a constant. However, it is not correct. Okay, it is not correct. Oh, okay. Anyway, we're gonna look into some mathematics of this lubrication issue later. Okay, and this is the units of viscosity. Okay, so the most commonly used is the CGS units we call the poise or the CP, center poise. Okay, and we can define the conversion from the CGS to SI units. Okay, SI units. Okay, and the IPS units, the microradian. Microradian is often convenient. Okay. So okay, I'm not gonna explain this a lot because it's just a units, or you can just study by yourself. Okay, you can just figure it out by yourself. Okay. Okay, so for this mechanical design, most of this components, most of the components or the machine is by experiment. Okay, so we use experiment to build up the chart or table for the future design. It's the same for the lubricant. The lubricant. Okay, so we define the lubricant type SAE 70, SAE 60, SAE 50, and so on. And we run experiment at different temperature. We say the average temperature. Okay, average temperature. And then we figure out what is its viscosity is. Okay, and then we can build up this charge. Okay, and this is the US units, and this is the SI unit. Okay, and remember this chart is a log-log plot. We say it's from this road experimental data, it's an exponential plot, right? After we take the log, we just plot this in log-log graph. It will become a linear, like this, like what we saw here. Okay. Okay. So we can just fitting this, right? We can convert this to an exponential function, right? We can convert this into a linear function, right? So we can fit in this curve. Okay. Okay, so this curve is fitting by this equation by log-log graph. Okay, so here, let's see some samples of the different oil, lubricant oil, like here, the 20W50 here. It's a type of the multi-grade engine oil, meaning its viscosity changing with temperature. And the W stands for the winter, and the number refer to the oil's thickness at different temperature. And the 50 represents the SAE 50. So it represents the SAE 50 here. So this 50, SAE 70, you'll see the mixed grade oil will be this two-digit number will be 70. And winter. Okay, and the winter. And the winter. And the thickness at that winter. Sorry, at that temperature. Anyway, that condition. Okay. Okay, so this for the experiment of different oil brand. Okay, and different type of the materials. Okay. Okay, so when we take the log graph, this line will become linear. Okay, will become linear. Okay, so the oil outlet temperature and the effective viscosity. Determination of the oil outlet temperature is trial-and-error process, right? So I mentioned previously, for this machine design, most of these, the former engineering scientists already built up a lot of the experimental data. Okay, from our point of view, right now, we think, okay, we can build up the AI, right, database, right? Okay. Okay, so if we go back to that age, we'll look at how they define those parameters, such as oil temperature. Okay, it's a trial and error. Okay, so first estimate the temperature rise to determine the viscosity and use this viscosity, right? We estimate the temperature rise to determine the viscosity, right? Like that plot, we already saw it, right? And use the viscosity to perform the analysis and compute the temperature rise. Keep repeating. Okay, we know the viscosity. or we get the temperature, and we determine the viscosity. And we get the viscosity, and then we just to perform the analysis to compute the temperature rates and repeat till the estimated and the computed temperature agree. Okay, and it determine the viscosity use the temperature that is average of the inlet and outlet temperature, TAB, average. Okay, so how to define the viscosity temperature? It's the average temperature. We define the lubricant temperature by using the average of the inlet and the outlet temperature. Equal to T1. T1 is the inlet temperature. Delta T is the temperature raise from inlet to outlet. Okay. So the curve fits the viscosity temperature chart, right? This is the curve fit, approximate curve fit given by this. By experiment, we figure out, okay, so the viscosity and the temperature relations has this function from experiment. Okay, from experiment. It's an exponential function. And we take the log graph of this equation, we get the linear function, linear equation, right? So the previous few pages, we already showed that. Okay, so, and then we can base on this approximate curve to figure out the materials, the oil materials type corresponding to the mu naught. It's a constant, and the constant B, right? Okay. We define this is SAE10, SAE20, SAE30, SAE40, and we figure out by this approximate curve to find the mu naught and the B. Okay, so therefore say, okay, for this SAE10, the oil, whose mu naught is 0.0158 times 10 to the power of minus 6. And it's the constant B is 1157.5 Fahrenheit. Okay. Okay, so Patrick's equation for the bearing. So if you still remember this model that I mentioned previously, there's a plate, right, on a river, and we apply force to push or to draw the plate. And this the lowercase u represents the velocity profile, right, of the liquid or of the fluid. So we can just model it for our journal bearing. Okay, we can define the plate is as the journal or the shaft, right? And the bottom of the river is we'll say the bushing, or we say it's a bearing. Okay, and the gap between these two is the thickness of the lubricant, right? And for this model, it has the constant velocity u, right? It's a linear velocity. And we can convert it to a journal bearing with the angular velocity, with the speed is n RPM, n RPM. And this velocity profile, if we look into an infinitesimal element here, right? So we can just model this journal bearing, the thickness of this lubricant has this velocity profile, right? We can look at this velocity profile, which is the same as this velocity profile. Therefore, we can use the shear stress, or say the Newtonian fluidic equation, right? to model this journal bearing, right? To model the journal bearing. Okay, so in this case, we define the velocity here, the velocity profile here, right? We'll define the velocity profile here, the gap, within the gap, okay? Within the gap, okay? Within the gap. Okay, so any problems? Okay, so we define the L is the length of the bearing, the length of the bearing, okay? The length of the bearing. If we neglect the side leakage, okay, so you can see how to define the Patrick's equation for this journal bearing without the side leakage. Okay, so let's go back to this model, right? So now we just think of this clearance H is the radial clearance between two surfaces, the journal and the bearing, the shaft and the bearing, the shaft and the bushing, right? So the C clearance represents the distance between these two surfaces, right? Okay. As I mentioned, this velocity distribution du dy equals to the u, the velocity of the plate divided by the clearance C, right? Clearance C. Okay. And then we times the radius of the shaft, the shear stress times the radius of the shaft, right? The shear stress is represented as this, this is the shear stress. It's a tangential force, tangential stress, okay? Shear stress. It's the opposite direction to that rotating speed, N. Okay, so this stress times the R, and for this right-hand side, we also times R. So we times R on both sides, right? And then this shear stress equals to the force divided by the area. The force, right? This is the force here. The force here. Okay, and the force times R equals to T. T is torque. Okay, the torque divided by the area. So what is the 2 pi RL is? What is the 2 pi RL? That's the contact area of the bushing or the bearing. Okay, so if we go back to the previous, okay, so it's the this area. If we draw it a 3D, it will be looking to like this, right? So however, it's not like in this case, it's the tube, right? It's a tube shape. It's a tube shape. Okay, it's a tube shape. Okay, so we can just extend it as the rectangular plate, and then we can calculate this area. Okay, and we can calculate this area and this area. Okay. Okay, so this defines this area 2 pi RL equals to mu times the u equals to 2 pi R n. The velocity, constant velocity u equals to 2 pi R times the RPM. Okay, time RPM. Okay, so we can rearrange this equation, right? So this area moved to the right side. We got the torque, right? The torque equals to this term. Okay, so let's go back to the definition of the friction coefficient F equals to the force, the tangential force divided by the normal force, right? F equals to the friction coefficient times the normal force. Therefore, the friction coefficient equals to the tangential force divided by the normal force. Okay. And this tangential force equals to the torque divided by R. Okay. Torque divided by R. And the normal force is the weight. Okay. It's the load. It's the load. It's the load. Okay. Therefore, say the torque here, right, equals to F is the friction coefficient times the the load, okay, the normal force times the radius of the journal. Okay, and then we can plug this torque to here, right? Okay, therefore FWR equals to this term. Okay. Okay, so for this distribution load applied to this shaft, no matter which direction, okay, it doesn't matter because this the bearing actually wrap this shaft, right? So when it's rotating, this distribution, this pressure distribution can be either direction. Can be either direction. Okay, so for this okay, so for the direction of the loading given the original, I would be more accurate if I had showed this pressure acting on the bottom of the journal, pointing up. This reverse of the direction does not cause an arrow incongruity. Okay, so we can define any direction. Okay, so I can say, okay, so maybe we can define uh uh right, right, it's try point up. It's the same. Okay, it's the same. Okay, so let's go back. So this is what we get, right, from the previous slide. Okay, so the W is going down, and for this bearing is have the reaction force W point up, point up. But it doesn't matter. Okay, it doesn't matter. Okay, so this is what we get. Okay, so the F, still F. The W is the load, right? The W equals to the P, the pressure times the area. Area equals to 2R times L times the P. Right? So we can just by using the PL2R here. Okay, times R. Right? Okay, and then we rearrange this equation to figure what is the friction coefficient is. Right? We just remove all the things to the right, and we get the friction coefficient. Okay, so the friction coefficient and this equation is called the Patrick's equation. Okay, and N here is defines the RPM, right? Rotation per minute. Okay, and the mu here is the par times the second is the SI unit. It's the SI unit. Okay, so let's ask you guys some questions. What's the problem of the Patrick's equation? Right? We use this Newtonian fluidic equation, okay, the tau equals to mu times the du dy to derive the Patrick's equation. And from this equation, do you guys discover any problem or any error of this equation? Okay, so my course will stop here, and you can think of what's the issues of this equation is. Okay, and then we can discuss next time. Okay, we can discuss next time. And the answer I already mentioned previously.